Now let's analyze how to calculate the direct expression of Fibonacci numbers. Of course, for Fibonacci numbers, there are a lot of ways to calculate its direct expression. Here, we would introduce the method using generating functions. And first, we need to have a generating function. Here we use gx to represent a Fibonacci number. A generating function is to use a sequence of the coefficients of x to the kth power. Here, because we know that f0 is equal to 0, we add from f1x to f2x squared. Keep accumulating. Well, actually this is the generating function of Fibonacci number. If we could calculate the expression, then we could find out its coefficient sequence. So let's analyze it. When we introduce the Hightower problem, we add the terms one by one to find the expression of gx. We could use the same method here. Let's start from x to the third power. The coefficient of x to the third power is f3. By the recurrence relation f3 equal to f2 plus f1, the coefficient of x to the fourth power is f4. It's equal to f3 plus f2. Adding all these terms, we get a sequence whose left-hand side is the same as gx, except the lack of the first two terms. So the left-hand side is gx minus x squared minus x. Because of that, the coefficient of y, f1 and f2 are both 1. Here, we ignore them. What about the right-hand side? Actually, there are two terms. Let's analyze them separately. So for instance here, f2 should be multiplied with x to the third power. f1 should also be multiplied by x to the third power. For x, f3 times x to the fourth power in the original generating function, f2 is corresponding to x squared. f3 is corresponding to x to the third power. So in this adding process, there is one more x. So after taking x out, what's missing? Well, it becomes f2 times x squared plus f3 times x to the third power. Compared with the original generating function, only the first term is missing. So the first part of the right-hand side is actually x times gx minus x. What about the second part? The second part becomes f1 times x to the third power, f2 times x to the fourth power, so forth. Comparing with the original gx, actually it has x squared multiplied. So the sum of the right-hand side should be equal to x squared times gx. So now we've got the equation about gx. So what's gx like? Let's simplify it at first. It's 1 minus x squared times gx equal to x. So the answer is gx equal to x over 1 minus x squared. And here we want to expand it to a sum of two fractions. So we need to perform some transformation on the denominators. To write it in a form of 1 minus alpha x, here 1 minus x squared is exactly equal to 1 minus square root of 5 times x over 2 times 1 minus 1 plus square root of 5 times x over 2. Now we use the same method as the one we used for Hightower to convert it into a sum of two fractions. The denominators of the fractions are exactly the factors here. For example, this denominator is 1 minus 1 plus square root of 5 times x over 2. What about the numerator of this fraction? We don't know. So we denote it with a and make it an undetermined coefficient. Then we will find it by solving equations. The other term is b over 1 minus square root of 5x divided by 2. Of course, b is also an undetermined coefficient. The two undetermined coefficients a and b could be solved with the following equation. This expression is equal to x divided by 1 minus x squared. So what are the values of a and b? We could solve it now. The numerator corresponds to a plus b is x. So its constant coefficient should be 0. And its first order coefficient is just the square root of 5 over 2 times a minus b equal to 1. So by solving this equation group, we now have a plus b equal to 0, well, a minus b equal to 2 over the square root of 5. So a equal to 1 over square root of 5, b equal to minus 1 over square root of 5. Now we know a and b, so we would also know the value of gx. Plug in a and b, gx equal to 1 over square root of 5, 1 over 1 minus 1 plus square root of 5 times x over 2, minus 1 over 1 minus square root of 5, 1 minus square root of 5x divided by 2. Now we know that we could expand it to alpha to the kth power x to the kth power with Taylor expansion. This coefficient could be converted to beta to the nth power times x to the nth power. Here, in order to be convenient, we denote 1 plus square root of 5 divided by 2 with alpha, denote 1 minus square root of 5 over 2 with beta. So this expression becomes a sum of multiple terms, which is 1 over square root of 5 times alpha minus beta to times x plus x squared minus beta squared times x squared, so on and so forth. Now we've introduced alpha and beta and it's simplified to write gx. The corresponding coefficients are the Fibonacci sequence. Here fn are the coefficient of each x to the nth power in gx. It's 1 over square root of 5 times alpha to the nth power minus beta to the nth power. Plug in alpha equal to 1 plus square root of 5 over 2. Beta is equal to 1 minus square root of 5 over 2. So now we could find the nth Fibonacci number is 1 over square root of 5 times 1 plus square root of 5 divided by 2 to the nth power minus 1 minus square root of 5 over 2 to the nth power. Here we've discovered that we get the corresponding expansion of Fibonacci number. A magic thing is that if we divide the nth Fibonacci number by the n minus 1th Fibonacci number, which is derived by plugging in n and n minus 1 to this expression, after simplifying, it's actually 1 plus square root divided by 2. What's that? It's a golden ratio, 1.618. Well, we just find the direct expression of Fibonacci sequence. We could find that the recurrence relation of Fibonacci number is simple. Fn equal to Fn minus 1 plus Fn minus 2. But the expression we got contains a lot of square roots. Well, Fn is an integer, but we use some irrational numbers in the direct expression to denote it. So Fibonacci numbers create a relationship between natural numbers and irrational numbers. What's more magic is that the ratio of adjacent two Fibonacci numbers, Fn and Fn minus 1, exactly the golden ratio. Actually, the golden ratio could also be denoted with this infinite fraction. We now know that although there are a lot of forms in mathematics, they are closely related. Well, if we permute the fraction like the Fibonacci sequence, we could get such a golden ratio curve. And in our real life, we will see that there are a lot of golden sections in the natural world. So Fibonacci numbers are really magic. And they are widely applied in our real life.